All right, so welcome everybody. This is the second hackathon teaming meeting for the 2023 CompuCell3D Workshop. Just need to go ahead and let everybody know in advance of this workshop or this session and the workshop, but this session today is being live streamed, recorded, and will be distributed on YouTube after the fact. So just so you are aware, this is being recorded and streamed online. This slide deck for today, which is pretty much the same as last week, is available in the student materials folder. Find the link here. I'll put these links in the chat as I go. So if there's weird pauses, I'm looking up links. So into the student materials folder. You can submit any questions, concerns, suggestions you have along the way via the Zoom chat, but we will have open time for questions at the end of the intro portion here. We won't have any breakout rooms today. This is just our boilerplate template for the workshop slides. If you have not joined the Slack yet, please be sure to do so using the following link. So this link has been updated. Slack links stale every 30 days. So this is the new link that you will need to use to join the Slack. If you already have the link from before, it will not work anymore. So you'll need this link for the next 30 days. And I'll post that again at the end for anybody who missed it or comes in later. One last note, please do take some time in advance of the workshop. So you have about a week left to ensure that you have a working NanoHub account and to download and install CompuCell3D to your desktop if you plan to run it locally. We recommend doing both, having a local install and having a NanoHub account ready so that if something goes wrong with your local install and we don't have time to fix it during the workshop, you can use the NanoHub app as a backup. You can just open projects from your computer in NanoHub. We'll show you how to do that in day one of the workshop. So it's good to have for backup and vice versa. If NanoHub starts going wrong, it's good to have it on your local computer so you can use it that way. And please do contact us as soon as possible this week with any questions you have, if there's any issues that you're encountering with installation. We've heard from a few people about having difficulty getting through the example from the orientation on NanoHub. Plan is to put together a short tutorial on that today or tomorrow and send that out. So we've gotten the version 4 CompuCell stuff fixed on NanoHub, so we should be able to walk you through the example from the orientation using the proper tool now. So I'll send an email out about that probably tomorrow once that goes live. So to jump back into our hackathon details, this is going to be repeated information for a number of people in the room, but for those who weren't able to attend the first week, we're just going to go over it again. Our hackathon this year is taking place after the second week of the workshop on August 12th and August 13th, Saturday and Sunday. Go over the schedule for that in a couple of slides here. But today is our second hackathon project pitch meeting. So for those who have presentations ready, I'll get a show of hands in a minute about who is going to present today. Lightning talks of 3 to 5 minutes. We weren't going to be super strict. I guess it depends on the number of people who are trying to present today, but we'll have the full hour at the end to do presentations. Like I said, your short presentation, sent the template out if you're using the template about the problem you want to model. Once you're finished today, please do upload your project pitch to the shared folder, which should be, don't have it in my quick list of links. I'll get that in a minute for you to upload to. Once we're finished presenting, I'll send the link out of where you should upload. And then we will be available both before and during the workshop to help scope your ideas into feasible CompuCell projects before we move forward. So if you do have an idea that you feel is too big or you're not sure how to implement yet in CompuCell, we're available to help discuss that over the next couple of weeks. And we will have some time built into particularly the second week of the workshop to help you kind of work through that process and find teammates after these meetings. For organizing teams, if you're not sure what you want to participate or which group you want to join, but you do want to participate in the hackathon, you're welcome to choose your top 3 projects and let us know, and we can help place you with those. Either if you're having trouble getting in touch with the group members, or if you're just not sure which group you'd like to be, we can help you find a group. And we will be helping to suggest teams of everybody who's interested in participating in the hackathon at the end of the week on Friday, August 11th, if you're not already on the team. So don't worry if you haven't found a team by the end of the workshop, we will help place you. Or we can help you find a project that may only need 1 or 2 people to do if you'd prefer to work alone, if you're having trouble finding a team with a project you're interested in. And please do work through the Slack channels to find groups. We found that the Slack is a good place for people to talk about hackathon grouping. So we will be assisting with that as we go forward, but a lot of that is largely self-organized. So I know I mispronounced your name last time. It's Akinwale, right? You got your hand up?
Yes.
Okay, good.
I have a question.
Sure.
Because I'd like to know the link to the shared folder where I will upload my hackathon pitch.
Yes, I will grab that shortly and send that out in the chat.
Okay, thank you.
I didn't have it in my quick list and it'll take me a minute to find it. So I'll send that out before people present today.
Okay, thank you.
Yep, thank you. So just a little bit of what the hackathon will look like. It's going to be mostly open work time, but we will have check-ins in the morning and at noon with the whole group to kind of see how people are progressing on their projects. And in the evenings, you'll have a brief. Here it says written. We just have a formal template with some questions for each group to answer. You won't actually have to be doing any big writing during the hackathon. We know that takes up time. So it's more of a formal verbal report of where you are and what you need help with so that we can have feedback for you for the next day. That's especially important on Saturday night. So make sure that when you are working on your project that you're keeping notes about any issues that you've encountered that you need help with. And we can help you as much as possible during the day, but it's good to know what people need going into the next day so we know what to do to prepare in the evening as people continue to work. And then at the end of Sunday, we will have a short oral presentation and model walkthrough from each group. So kind of present your entire model, and we'll have you talk about a couple of different things, particularly issues that you encountered, how you overcame them, just a sort of short presentation from each group so that we can all learn a little bit from each other because everybody's project tends to be pretty different. And then as an additional note here, there will be post-hackathon support with CompuCell team available after the workshop. So if this is something that you'd like to turn into either a thesis project or a publication, we are available after the workshop sort of indefinitely to help you turn your hackathon projects into more either official NanoHub apps, like we said, publications, or if you're using this for your thesis, we are available to help answer questions on that as well. Just some basic expectations here going into the hackathon. We do want everybody to have some idea of what they want to model and why. If you're not looking to lead a project, then some idea of kind of what you're interested in working on is useful. So we can either help place you, and it also helps you find a group yourself. And then you also need a shareable description of yourself and your skill set / background. Again, it's okay if you're a beginner. It's important for everybody to sort of know that, but still, even beginners have skills that are useful to groups. You know, it's often difficult to self-assess what may be useful, but somebody else may be able to quickly identify what's useful to them or to their group. So it's always good to have a short list of kind of things that you feel you have some level of expertise or at least experience in. We have a shared hackathon teaming document for you to do that. I'll walk through how to do that in just a minute. But having something that you can send to someone if they say, you know, we're interested in you joining our group, can you send us your skills list? It's very useful to have something ready that you can just send out because the workshop's going to move quick. And there will be some time for teaming, but it still can be a little bit tricky when the workshop is still in full swing. Expectations you can have of us: we will be available for questions and assistance throughout the hackathon. We're going to be available not 24/7, but for most of the day, both Saturday and Sunday, to help groups with their projects. And again, after the hackathon, we are perfectly happy to continue helping people with expanding their projects once they've gotten started on them. One other note here: if you intend to participate in the hackathon, a little bit of Python background will be useful. So we have the site that we like to send people to, these Rosalind training exercises. Let me grab the link here for the chat. You should be able to complete exercises 1 through 5. You don't have to prove to us that you can complete them. It's just a good way of self-assessing whether your Python skills kind of will be ready for the hackathon. There's actually 6 exercises here. The 6th one is not as necessary. So exercises 1 through 5 will show you if you're ready to go. We recommend trying those sometime this week if you have the time, because if you realize that maybe you're having trouble getting through them, we do have the 1-day Python boot camp on July 31st, this coming Monday. So we do recommend that if your Python is rusty or if you don't have any background in Python, that you do come to that boot camp, and it will give you all the basic skills you need to participate in the hackathon. So for teaming, again, please do join the Slack if you have not yet. I'll post this link again here. A couple people come in since we started. There's the Slack link. And please also post your project ideas to the shared teaming document. Again, we'll upload your project pitch to the hackathon folder. I'll get that link in a minute. Can't copy it easily. Actually, yes, I can. Let me just do that before I forget. I'll post this again once people have presented. So there's the link to the folder where you should upload your presentations. And for those who maybe have an idea but weren't ready to present today, if you would still like to put together a couple of slides that you can upload to the folder for people to reference later. The Lightning Talk template can be found here at this link. So one thing I do want to do before we move on is I want to look at this teaming document together briefly. Let me reshare my browser here. So it looks like we've got a couple people populating this already. There's always a little bit of confusion about how to use this document. So we're going to go over it today. Basically, we have a couple of links here. I need to add the Slack channel to the Hackathon Slack channel link. That'll be my homework. You can leave the breakout room names alone. This is for once we actually have hackathon groups formed. So I'm actually going to put ignore for now, so it doesn't confuse too many people. But what we're really looking at here is if you have a hackathon idea, please put your name at the bottom of this list. So we have the format here. You would put your name, your email, and a descriptive project title. And that's all. If you have a project idea, that's all you need to put here. If you're looking for projects to join, then you would put your name, your email, a short list of research interests, and then your skills after that. So just, again, a short list of relevant skills that you think might be useful to a number of different projects. If you did have a project idea, we do ask that you make a separate, looks like something has happened here with page breaking, that you make a page for your project. So you have an example project description format. So what you'll do, leave this particular page alone. You'll go to the bottom and do Control-Enter to make a separate page. And then you'll copy and paste this in. So I'm actually just going to do that now for whoever wants to go first. So you'll just get to this line, Control-Enter, then paste. Take that out. Then you'll just put your name, title of your project. We'll need a brief description. So this is, you can be longer here than you were in the first page. Then you'll want a list of expertises that you're seeking in partners. So if you need, so for example, if you're a experimental biologist looking to model a problem and you don't have much background in computation or in programming, you would need to put that you are looking for someone who, you know, is a Python expert, maybe someone who has experience in computation. If you're the computationalist, you would list, you need somebody maybe who has Python background, or maybe someone who's more familiar with biological methods. So basically whatever you feel you need from other group members, you would put here. Appropriate models to use. James, do you remember what this was? I'm suddenly confused by our own template here, sorry.
So that's to talk about what kind of modeling you want. In other words, is it a multicellular model? Is it a field model? Are there existing models of this that you could adapt?
Gotcha. Okay.
What modeling exists now, or do you think is appropriate to use to solve the problem?
Yes. Okay. So that's, yeah. So it's basically a description of what kind of model you're trying to build. And if there is literature that this model is based on, posting a link here to that would be very useful. So people interested in your project can go get the paper and read up on some of it. If you have the paper and it's behind a paywall, maybe we will think about making a folder for people to upload papers that their projects are based on. That way people have access to it. I'll make a note of that here. And you want to list how potential partners should contact you, your preferred email. It's good to provide a phone number. Things get a little bit wonky with time zones during the hackathon. Sometimes the asynchronous nature of email makes things a little bit tricky. So please do provide your phone number so people can get in touch with you that way. And if you have any additional, if you use WhatsApp or any personal communication methods, do provide that information here. Once group members start to join, so once people have talked to you and you've decided to work together in the group, you'll put your group members' names here. So we know that people have already found a group. And here, this section, you'll leave blank. These is for us to come in and leave some comments on your project description, just to kind of point out any areas where we think it might be good to do some additional scoping, some additional background reading, or if we think there may be any potential challenges that you'll face with CompuCell, we can give you a heads up in this comment section. Any questions about that before we move on? Once this document starts to become populated, it'll be a little bit more clear about how people are using it. It tends to be a little bit different from year to year. But that's the basic overview.
Yes, I have a question.
Go ahead.
Yes, then my question here is this. After I have filled everything is completed, how can I submit it to you to view it?
Once you've filled out this document?
Yes.
Yeah, we will be checking this periodically, probably at the end of each day.
Okay.
It's a Google Doc, so it's shared.
Yeah, so
Okay.
yeah,
You don't have to submit it. It's automatic.
Yeah, that's actually, that's a good question. I didn't say that. So thank you. That's good to be explicit about these things. This is a shared Google document. Everybody will see all of the changes made to this.
Okay.
But if you would like more immediate feedback, please feel free to shoot me an email
Okay.
once you've filled it out, and we can take a look for you. I'll put my email here in the chat. But yeah, we will be checking this probably daily starting tomorrow.
Okay.
So just fill it out. You don't have to worry about submitting.
Okay.
Those kinds of questions are always very useful. So thank you. Revealing my assumptions about how clear things were. Any other questions about the shared document? Chat here, so I don't miss anything. Okay, so if there are no other questions about that, I think we'll go ahead and move on. And again, if you have questions about this, feel free to continue to ask them after we've moved on in the chat. We can always circle back around. We have a little bit of time today. So for the overall hackathon schedule, again, it's going to be 2 days of hard work. Day one, so for Saturday, we'll spend probably, so we start at 10 both days. Obviously, groups can work at whatever times they feel is necessary to get through their project. But we will officially start each meeting at 10 o'clock each day. First hour of day one will be spent just finishing up with self-organizing the teams. It's usually still a few people who need to be placed, or a couple of people who maybe need are looking to be moved, or things like that if groups have gotten too big. So we spend the first hour just finishing up with organizing teams. Then you'll have a 3-hour block of getting started on your projects. So we recommend spending this on initial setup and parameterization of the model, making sure that everybody's on the same page, everybody knows what they're supposed to be doing. That takes a good bit of time. So we recommend using this block for that. If you're already ready to go and you've been talking to your group members all week, obviously you can use the time to do whatever you feel is needed. But please don't skip the initial setup phase of making sure that your group is all on the same page. Things can tend to get a little bit out of hand pretty quickly if there's some miscommunications early on with these 2-day projects. And again, we are always available to help with that kind of thing as well, if you need some additional assistance with that. From 1 to 1:30, we'll have a quick check-in in the main session with each group. So this is just to get a feel for how the morning has gone for everybody. You don't need to have any formalized presentations or anything for that. We'll just ask each group, and you'll kind of go around and report in on how things are going so far. Then there will be a 3.5-hour block in the afternoon for continued work. And again, this is work with the CompuCell team available to help. You'll probably need to continue working in the evening to get your projects up and running. But we will be available and circulating to help people during the afternoon work session. And then from 5:30 to 6, we'll have, again, a half-hour check-in to see how things are going at the end of the day and find out what people need going into day 2. So for day 2, again, we'll start at 10. We'll have a quick 30-minute check-in because some work will be happening after we leave for the day. We'll just see how things went overnight, basically. And then you'll have from 10:30 to 2 to work on your models. This is a big work session. Again, we'll do a check-in from 2 to 2:30 on how things are going of your afternoon work block. And then we'll have an hour for reports and discussion of how things have gone. And getting feedback from people about maybe what they need moving forward with their projects if they're planning on continuing to work on this after the fact. So you'll notice there's no scheduled lunch breaks here. Lunch will kind of be up to each group to determine. Groups tend to be coming from various time zones. So that will be an additional logistical challenge that will need to be addressed, is how each group is going to manage if people are coming from vastly different time zones. So we don't really have a good time for lunch, considering that everybody is all over the world with this. So meals and breaks and when people are going to manage to find time to sleep will kind of be up to each group to determine on their own. It gets a little bit tricky with scheduling, but it's also a little bit of a benefit because it means that typically one person in your group will be awake and will be able to continue working on things while the rest of the group gets some shut-eye.
Yeah, Hayden, can I ask a question? I imagine you've had this work at Hackathon before in the past. So what has been your experience with regard to scheduling?
So this is my second time running the workshop. James is more familiar with this on the long-term scale. But last year, most of the groups managed their scheduling challenges fairly well. Again, this is, I don't mean to make it sound, it's definitely 2 days of intense work in order to get your model working, but it is very sort of casual work. We don't have any huge expectations coming out of the hackathon. We do want everybody to have at least a working prototype of their model by the end of it. But each group is kind of free to take breaks as they need to get things organized. It's a little bit difficult to say, exactly how scheduling will work with each group until we know what each group looks like. But last year we didn't really have any big problems with the time zone differences.
People typically don't get a lot of sleep for those 2 days. But it's up to you. I mean, you put in as many hours as you feel like and the times you feel are appropriate. The main thing is that we're available to help during particular windows of time. So if you want help, if you email us or Slack outside of those times, we'll do our best to respond, but we're not necessarily there on the spot all the time. Whereas during the working days, we're there to answer questions or work and brainstorm with people on demand.
Yeah, the people on our team tend to keep slightly different hours as well. So again, if you do send us emails, we may be able to respond to them, but we can't guarantee, after 6 o'clock that we'll be able to get back to you in a timely manner. So yeah, it'll just depend on kind of the makeup of your group. Sometimes we have groups that are all kind of within the same relative window. We've had a couple of groups last year that were on opposite sides of the planet, and they still managed to get a lot of good work done. So
Yeah, thanks.
Yeah, so like I said, once the groups start to form that second week, we can be a little bit more helpful with that kind of stuff. Right now, it's all kind of theoretical and vague, so it's a little bit hard to say how it'll go. But we're happy to help with teaming, and if there's scheduling concerns, we can certainly offer advice once the groups are more solid. So we talked about this a little bit in the last week's meeting. This is if you are interested in participating in the hackathon and maybe even in leading a project team, but you don't have a clear project idea yet, we do have a list of papers that we think are good candidates for reproduction in CompuCell. So if you want to take a little bit of the conceptual heavy lifting out on the biological side and use a model that's already been developed in either a different software or something that we think is good for representation in CompuCell, maybe that wasn't previously modeled. We do have this list of projects online. Let me go grab the link for that. Put that in the chat. You can take a look through some of these, and if anything piques your interest, like I said, we think all of these papers are good candidates for reproduction in CompuCell, and it's a good way to get started on a project without having to start from scratch. We think that most of these papers could probably be reproduced by a group of maybe 2 people, 2, 3, maybe. But like I said, it's a good way to kind of cut out some of the early work of getting the project scoped and manageable in CompuCell. So if you have maybe someone you're interested in working with, but you don't have a project yet, we recommend taking a look through these papers as a starting point. I think that is all. Yes, that is all I have for the initial start, for the initial part of the meeting. I want to leave the floor open for a couple of minutes here for general questions people have about the hackathon. Any questions or concerns, either both about their project or logistically about how the hackathon works. So we'll probably wait a couple of minutes here in case people want to type questions into the chat, but also feel free to just unmute and ask here or raise your hand, and we will get around the room.
Yes, I have a question.
Mm-hmm.
I have a question.
Yeah, go ahead.
Yes, I have an idea. Work on beta cells interaction with the T helper cell for diabetic patients. But the challenge I'm facing here is this: my background is just physics, and I'm working on a computation of metals. So I don't know, how can I go about it? Is it advisable for me to continue with the idea, or I should just find a group and join? Because this is the idea I have, and I'm interested in that idea, but I don't know how should I even start with. This is the challenge I'm facing, because this is my first time of dealing with anything biological computation. The computation I did is just density functional theory for materials, other materials like metals and other things, not biological. So this is the first time I come in touch with anything biological computation, and I have this idea. to work, to see, to check, to analyze the interaction that leads to that issue of diabetic type 1, and then to see how I can at least come up with some reasons for why such thing is happening. But I don't know how to go about it. So please, what can you advise me? Am I in a good stand to like go with the project, or I should just join a group, even if the group is not in line with my own thoughts? That's the question I have.
So in a minute, I'll let James maybe address your particular project idea, but just from the, the dilemma of doing your own project or joining a group, that is ultimately up to you at the end of the day. If you feel that you are a disciplinary expert in this problem and you would like to lead a group, that's absolutely no problem, that you don't necessarily have the computational background. So, the workshop will prepare you for this project. You'll definitely be coming out of the workshop with much more computational background than you currently have. But even so, it's still fine if you would like to lead a project group just as the biological expert. So that's something that you would want to put in the teaming document, is that you're looking for people with, more computational background maybe than you feel you have now.
Right. Well, in this case, I think it goes the other direction. He's saying that he has the computational experience, but not the biology experience.
Oh yeah, sorry, you said you were in physics, so you don't have the biology.
And so what I would say is this, and this is a general thing, which is that trying to understand any biological problems are intrinsically very complicated. There are a lot of things that one has to learn about the systems to model them. Modeling isn't magic. And so you need, just the way if you're going to build a model of material, you need to know a lot of details about the material before you could build a computer simulation of it. In the same way, when you're trying to model a complex biological system, you have to make a lot of biologically meaningful decisions first. And the particular example you give, I think, is an excellent one. Fascinating problem, an important one. So there are existing models of both T cells in a variety of contexts and beta islet cells in the pancreas. I don't know if there are existing models of their interaction. In the case of diabetes, you have to have some hypothesis about why the T cells are targeting the beta islet cells in the pancreas. And if there isn't much known about that, then it's going to be difficult to build a model of what's going on. You could look, for example, at models of how T cells clear cancer cells in immune response to cancer, which could be an analogy. But I think you're right that to try to build from scratch a model of a very complex system like that would be challenging if you didn't have a significant biological background. And so there are two possibilities. One is that you find the team members who have strong biological backgrounds who are interested in the same problem, in which case you could provide the integration and the computational expertise, and they could provide the biological understanding and background. Or you could find an existing simulation or model of an aspect of that problem that you'd like to replicate that would help you understand the biology more. But you do have to know quite a bit about the biology of a problem before you build a simulation, because you're going to have to decide what are the cells, exactly what do they do quantitatively, how do they interact, what are the signals that are passed between them. Making those decisions is not trivial. And so in general, it's important, I think, to try to go from an open problem like, why do we get type 1 diabetes, to asking more and more specific problems. People have worked on, for example, T cell synapsing and recognition. People have worked on immune hiding. People have worked on T cell selection in the thymus or T cell selection in the lymph nodes. People have worked on antigen presentation. And so a high level problem like the origin of type 1 diabetes, you would want to break it down into more manageable subproblems. And this is what we do in physics all the time. When you're learning quantum mechanics, you start out by doing a square wall potential, then you do the hydrogen atom.
Yes.
So it's not that you don't want to understand how high temperature superconductors work, but you don't jump in at the deep end with that unless you find somebody who has a theory of it, and then you can understand it. And so I'm not trying to be discouraging, but I'm saying that if you haven't done biological modeling before, probably the thing to do would be to either find a model that's published that you want to study, which would be fine, or find a team that's doing something analogous to it. Some team that's working on T cells or immune response or beta islet cells. We've had people do beta islet cell interactions and synchronization before, or development problem of the pancreas or another organ, so that you can build up the components that you would need to do the kind of modeling that you want. I think the aim is great, but I think in 2 days or 3 days, you want to have something where you could have a solid achievement that you could show for the time you've put in.
Okay, thank you so much. Thank you.
Yeah, thanks for catching me on that, James. I heard you say you were a physicist, Mohammed, and then for some reason I answered a different question. So, yeah, I mean,
But I was
just
going to say the other thing you could do is you could put into the discussion document that you're interested in modeling in diabetes, type 1 diabetes, and ask people if they have anybody has expertise and interest in that topic. There might be people who have biological background who have interest in that, who are looking for a project. So then if you get the response from people, you work on that project. Otherwise, you find a project that you could join where you'll learn something related to it.
Okay. Okay, thank you.
Yeah, so this helps make a good general point as well, where if you have a project idea and you want to work on that project, you are sort of inherently the project leader, which means that you're going to have to do a lot of delegation. But in order to know how to delegate, you have to know what to delegate, and that requires a pretty decent understanding of the problem you're interested in solving, if the project is going to be successful in 2 days. But like James said, it's still definitely worth putting your project idea in the shared document, even if you're not sure if it's something you want to pursue or not. At the end of the day, it's not like if you put your project idea in there, we're going to make you do it. You're still welcome to join another group later if it doesn't pan out. But like James said, you may find someone who does have a decent understanding of this project who can help you with the scoping and the scaling, and maybe is familiar with the literature. It can help get you up to speed enough to run the project group.
Okay. Okay.
Any other questions? While we're giving people some thinking time, I do want to, by show of hands, see who all is interested in presenting a project pitch talk today. So we got one. Yeah, if you could just raise your hand. Give people a minute to find the mode. If you're joining through browser or anything like that, you can also just put in the chat that you have a presentation today. I know sometimes there's issues with emotes. If your Zoom client is even one half version out of date, sometimes it won't let you do certain things. So also welcome just to put in the chat. Looks like we've got 2. Any other project pitch presentations today?
Sharon has her hand up, I think, and Kuzume.
Yeah, my next 3. And then my next question was going to be if anybody has project ideas that maybe they don't have a presentation ready for, but they would like to discuss today. Go ahead and put your hand up as well. I'm just getting a feel for how much time we should allot for each talk, basically. I have a question in the chat from Solomon. Can you resend the links to learn the basics? Solomon, yes, if you will hang on until the end of the meeting, I can send those, or I can send them to you by email. I'll put them in a link or in an email rather to everyone as well before the workshop. I can do that tonight after this meeting. But yes, I can send you those links shortly, Solomon. Okay, so it looks like we've got about 4 people who want to talk about a project idea today. Does anybody have to go soon? Is anybody pressed for time today? I want to make sure that everybody who wants to present today has a chance. So if you need to leave early, please let me know now and we can have you go first. Looks like everybody is good to go. So we will just go in the order that people have their hands up. So once you start, you can just put your hand down. So Sharon, I guess we'll start with you. Let me go ahead and stop my share. Sharon can take over.
Okay. Let's see here.
And we have plenty of time today, so we don't have to be super strict about time, but roughly 5 minutes is what we kind of plan for. So we have plenty of time for discussion after.
Okay. And you can see this, folks?
Yes.
Okay. So this is not a very polished PowerPoint presentation. I've been thinking about it over the last hour in terms of specific presentation, although for many years in the back of my mind as something I would like to do. So evolution, not probably what most people come here looking for, since this is very biomedically oriented, but so let's see here. Maybe I should just go to the next slide. So I want to evolve something in CC3D. As it says there in the first paragraph, population of simulated cells in a simulated environment using natural selection. Can we evolve it to adapt to environmental challenges? Components of that would be a mixed population of different cell types. If you have no familiarity with CompuCell3D, you'll find out there are cell types, but those will be the species essentially. Built-in reproduction, have a genome, because you can't do evolution without a genome, but that doesn't mean it has to be very realistic. It's just a set of information that describes the organism. So that might just be the parameters that are built into CC3D for describing cells, or other configuration that we could add as we go. And mutation to change that during reproduction, and then have an environment in which there are challenges. So cells would have to survive. It could be something as simple as resource depletion and competition. And I wrote predation there because I'm wondering if it's possible to make CC3D cells eat other CC3D cells. But this is pretty open-ended. It's also, I would say, probably more than a 2-day project. So as I wrote in my last bullet point, the goal there is the famous MVP, minimum viable product. If I just evolve something in 2 days, I'll be very thrilled. And if other people join me in this, it could be bent to our interests, because I'm not specifically fixed on exactly what it is that needs to evolve. The motivation, though, I'm an evolutionary developmental biologist, so I'm interested in the evolution of embryo development itself, and also the evolution of body plans. And if you look at my there, I didn't have a picture, but if you look at my my avatar there, that's a starfish juvenile, recently metamorphosed, and I worked on those and sea urchins in a previous in a previous postdoc, and you noticed it was 5-sided radially symmetrical, which is very different from you and me. So that's the body plan. How's the whole thing organized? And it's still a mystery where really how body plans arise. And because of their crazy body plan, those sea urchins and starfish were originally thought to be very, very distantly related and primitive. But it turned out that they're actually one of the closest relatives of vertebrates. So yeah, that's the kind of motivating question. I would like to have a simulated system in which one can observe these kinds of things evolving. It's a tall order. It's a lifelong project. So what I want to do today is, or this in this hackathon, is sort of like the pilot initial study. Now I want to talk about the field of artificial life, which is really a subset of computer science, sort of allied with artificial intelligence, but it's the goal to have biologically inspired computation, and really to create life in the computer. And there has been a lot of work attempting these kinds of things. There are many, many examples out there of evolving creatures in quotes, in a simulation. I'm very interested in this approach as a way to apply to real biology, which is not really the goal of most of its practitioners. There's plenty of computational biology, but it focuses it focuses very narrowly on a particular system, a set of cells, an organ, a tissue. And I'm sort of more interested in building a big picture model where simulating creatures really have to have everything they need to survive and have to deal with the world. So 2 big questions in artificial life, which are also something I will need. So I'm interested in, I studied animal development, like those starfish. So I would like to have a multicellular model, a model of multicellular organism. And it occurred to me long ago that I shouldn't build that, I should evolve it, because if I build it, all my preconceptions about multicellular organisms will be in there. And so I'd rather start with my preconceptions about single cell organisms and see if I can evolve multicellularity. Now that's something people in artificial life have tried and failed at. So it's not a small problem. The other thing that they have failed at is open-ended evolution. They have great evolving simulated systems that evolve all kinds of interesting features in their organisms, but then they kind of peter out and don't have a source of unending creativity the way real evolution does. So, like I said, probably not going to solve this in 2 days, but in terms of motivation, ultimately, this would be I want to build a system that would help me do real biology, and in the process, it would also be addressing these big issues in artificial life. So I think the impact would be big if I make progress on it. My sort of, oops, I didn't mean to do that. Can't highlight, can I? Right here, elemental units to simple not enough physics. My feeling about artificial life and the approach that they've had is that they are really into using the simplest possible units and showing how complexity can emerge from them. And that's great, and it's really cool. But I feel that the failure to come up with evolution of multicellularity and open-ended evolution is because their units are too simple. A lot of times they don't appreciate what biological organisms really are like and how they really have to grapple with a physical environment and physics and chemistry. So I think that bringing physics into it, biophysics, this is why I want to use a platform like this. And this is why I'm in James's lab, actually, trying to learn biophysics. So I want to see what we can put together and what that can turn into. Okay, quick. Why do you need quantitative modeling? What I just said, life approaches don't contain enough physics. What are you trying to predict? I want to avoid this, actually. This is not the typical, I guess it's not the typical kind of approach, because I do want that ultimately that surprise. What can we evolve? What can come out of this? For a 2-day project, it's simply, what are you trying to test? Can I do this? Can I get something to evolve? And broader impacts. Again, my ultimate goal is to really study evolution with this. But yeah, so the rest of these slides I mostly didn't touch. I will maybe add something later and upload it. Yeah, we'll add to this and that. So for potential teammates, what are your skills and background? I obviously have a lot of experience in doing actual lab biology, developmental biology. And I also have a software engineering background. I have the Python. So where stuff like the physics and the math I'm learning. And this whole idea of evolving creatures into computers, evolutionary computation, and I have no experience with that. So if anybody has experience with that and wants to join me, that would be absolutely fantastic. That's my weakest probably piece of this. Although I have an idea how it should go. Other than that, anybody who thinks that this is really cool and wants to join me would be welcome. And that's it.
Yeah, Hayden, can we ask questions now or wait later?
Yeah, no, please.
Yeah, Sharon, very interesting talk. I'm kind of curious. So when you talk about simulated cells, are you thinking maybe giving us some kind of characteristics like quorum sensing?
I'm sorry?
That kind of thing?
Quorum sensing.
Yes.
I don't know that much.
I'm just giving an example, like because the thing is, the physics won't happen by itself. You have to give it a little bit of physics and kick it, and then evolution takes over, and then you kind of realize new physics. Isn't that the strategy?
I didn't catch most of that. I'm sorry.
Okay, so
Yeah,
I said the thing is, you're trying to get some physics out of evolution, right? And I'm saying that the physics won't happen by itself, but you probably have to give it a little bit of physics to start with.
Well, I mean,
for example, quorum sensing, okay? And then you get the system to start evolving. Did you catch that? No?
yes. I mean, so CompuCell provides a lot of physics out of the box. And that's a large part of the motivation for doing something like this. I will definitely look up quorum sensing and learn more about it and get more about what you mean. It could, if we think that's an important initial component, we can think about how to build it in.
Yeah, quorum sensing essentially is, well, there have to be a critical mass for a group of cells to start acting in a certain way. That's what in general, you can think about quorum sensing.
Right. So typically you'd expect, so that's, yeah, I don't know if that's something easy to build in right at the beginning, unless we have cells that are maybe, well, let's put it this way. That's, there's a lower level of phenomenon that would build into that, which is things like, what can cells sense? What do they know about the other cells? Do they signal each other? These are sort of fundamental biological phenomena that, yeah, we need to go through like an inventory and say, what are the pieces that we need? I think once you have that, and then you have to deal with how will cells respond to those signals, you can get to quorum sensing. Yeah.
I think Sharon, those are both really good points. And quorum sensing actually is something that people have worked on in previous hackathons. But I think coming back to the question of what is it specifically you're trying to simulate, is actually important in this context as well, because in the real world you get certain things for free, namely the limitations and physics of the real world you get for free. When you're doing evolutionary models, one of the problems is that the trade-offs have to be put in. In other words, you can have the cells move arbitrarily fast. It doesn't cost them energy to move in the simulation. It only costs them energy to move if you tell them that they have energy, costs them energy to move.
Exactly.
And so those trade-offs have to be decided in advance. I mean, you can change them, of course, as you run the simulation, but nevertheless, you have to impose those trade-offs. They're not given to you for free.
Right. That's exactly right.
That makes evolutionary modeling a little more complicated, because you do have to decide in advance. You know, in biology, if there's a chemical in the environment, the cell will respond to it somehow, because the chemical will affect the cell in some way. Whereas in simulation, if you don't say that the chemical exists, it doesn't exist. If you don't say the cell responds to it, it doesn't respond to it.
That's right.
So you do have, so serendipity at the level of signal channels is harder to achieve in computation. And trade-offs are things that have to be put in explicitly. And so one does have to be careful when you do an evolutionary model that you put in enough components that the system can evolve.
Right. Exactly.
And so that's not trivial to do. It's not impossible, but it's not trivial.
Right.
And I always look at Larry Yeager's Polyworld as a great model for this, where he had relatively complex agents, relatively complex signaling between agents, and then he actually had little neural networks that controlled them. And so what evolved was the control system, where it's given some set of channels. What does the cell do in response, or the agent do in response to the channel? The other thing that can work well in evolutionary modeling, if you have a single cell type, I mean, evolution is driven by there being some sort of scarce resource. That scarce resource could be space, just how much physical room there is, could be nutrients of one sort or another. It could be avoidance of, could be safety, avoiding a toxin. There are many possibilities. But there has to be some scarce resource. And so thinking about what that is, in my experience in evolutionary models, having some kind of predator-prey system tends to work a little bit better in terms of getting rapid results, something that's non-trivial in evolution. Holland had the great word of mud for evolutionary systems which churn along and don't do anything interesting and don't do anything interesting and don't do anything interesting. And then suddenly there's some rare configuration which does something interesting. But this was more for autocatalytic strings, but you can wait a long time to find one of those. And so to have some idea of a system that's likely to produce interesting results, and what kinds of challenges and competition you want to allow, and signals. I think that may make it, the more you think about that before you start, I think the more likely you are to develop something that's fun.
Mhm.
I know Connor is very interested in this kind of thing.
In fact, I approached him about this early on, and unfortunately, he wasn't going to be available to participate, but he was very excited by the idea.
And Iran Agman from years ago. So it's a great problem, but I think it does. If you just jump in and say we're going to do evolution somehow, I think that you have a reasonable probability of getting frustrated. We did publish, at least in our group, one evolutionary model, which was the cancer evolution paper, with Gilberto, who's here, and who would love to continue that work.
Okay.
And there is a student at IU now who's doing the modeling the evolution of quorum sensing, and cheating versus cooperating. So if you have 3 quorum sensing bacteria, that when they quorum sense, they release a public good. Some cheat by never releasing the public good, which is cost. Some always release it even without the quorum signal. You can do that, but I think this is great. We should probably move on to another one now if there aren't other direct questions. But I think that's a great. Thank you for leading off. That was a great inspiration. Show you don't have to have everything nailed down to have a great idea and to talk about it. And I don't mean to cut off the discussion, but let's go around the room and then come back so everybody gets to say something.
All right. So I think next up we have Wally.
Good afternoon, sir. Good afternoon. Can you hear me, please?
Yes. Yeah.
Okay. Let me share my screen. Okay, so good afternoon. Good afternoon, everyone. My name is Akinwale Victor Famotere. I'm currently pursuing my master's degree in mathematics with a concentration in bioinformatics at Georgia State University. I'm working on a project involving retina pigment epithelium under the supervision of Dr. Yi Jiang. And my hackathon presentation is titled Scutoid in CC3D, Modeling 3D Epithelium. So the biological background. For the purpose of this hackathon talk, I'm going to limit my talk to RP. So epithelium, as we all know, is a very important tissue, which acts as a covering or lining of various bodily surfaces and cavities, and also helps in organ homeostasis. Due to the fact that I'm working on RP, the shape has been defined to be related to the honeycomb with hexagonal packings having a tight set-to-set junction. Changes to these RP structures are known to be unhealthy, and it's a common cause of sight loss, which is termed age macular degeneration, AMD, in aged people. Understanding the 3D anatomy of these RP cells would actually give us insights in understanding sight loss, especially in age-related macular degeneration. And I'm going to show the pictures in the next slide. And this can help in producing organoids. So the biological hypothesis, the distortion of RP structure has been known to be one of the major issues causing AMD, that is the age-related macular degeneration, and the presence of drusen, which may lead to physical separation between this RP layer and the photoreceptor cells, distorting the normal structure. Is responsible for the problem in the RP, which causes delay in waste removal and every other things. Then our major goal is just to, so this is the age-related macular degeneration where we have the adults not being able to see clearly or seeing blurry visions due to the distortion in the cell structure of these RPs. Our major goal is to model RP aging and repair, and also understand RP-mediated retinal degeneration. So we started this project earlier on, and I got some help from Dr. Sluka, Dr. James Sluka, and we were able to reproduce the 3D image of RP as shown on the left-hand side of this paper, the one I'm showing on the left-hand side. And however, the major challenge we're having now is to produce the regular basal surface, which is here and not the hexagonal shape we have at the basal for the current CompuCell3D image, and also the curved parts extending from the top through the lateral to the bottom. That is the actomyosin designed as a drum. So this is the first one I wish to work on the hackathon to be able to produce the regular surface of the basal surface and also the curvature, which extend from this top down to the bottom. Then, in addition to this, I'm proposing on working on the scutoid, a new shape of the epithelium, which was presented by a group of researchers led by Javier Buseta on curved epithelium. So modeling this particular shape also can help us explore how the inclusion of this novel geometry affects the packing and organization of RP cells in 3D environments, which could provide insights into how epithelial cells in various tissues achieve optimal packing and maintain tissue integrity, which is critical for their function and overall organ health. So this is just what I wish to work on during the hackathon. Then we have the resources here, the 3 resources I'm using here. Then the skills and background, I'm from a math background and I've taken an introductory course in systems biology. Also, I have a little understanding of the CompuCell3D itself and also Python programming language. I'm looking for individuals or people who have strong skills in computational modeling and simulation or proficient in CompuCell or Python programming. For example, if I have someone very proficient in Python programming, to some extent, I know how to work on the Python programming file into the CompuCell3D and get the results. And also anyone who is enthusiastic about working on this kind of projects can also join. Thank you.
That's great. Those are 2 slightly different problems.
Yes.
Was
yes,
there
yes.
one or the other that you wanted to focus on, do you think, or you're open to either one depending on what people's interests in?
Okay, I think for this, it really won't be an issue because we're almost done with the project itself. It's just the basal surface, the regular structure of the basal surface, and also the actomyosin acting as this drum. The curvature from the side, from the top to the bottom, is what we need to complete in this. The major project I'm proposing now is the scutoid. So we'll be needing much help here because nothing has been done on this at all.
So for the scutoids, what do you know, if anything, about the biomechanics of the surfaces? Are they under tension? Are they?
It's in a curved epithelial tissue. It's actually explained in a curved epithelial tissue how it's formed, the morphogenesis, invagination, and all that. It was explained in the research paper where we picked it from.
Right, but I'm asking, how much do you know about the mechanical properties the faces of these, each surface separately.
Okay. I know a little.
Have an actin cortex under the surface of the cell, right?
Yes.
And that has some rigidity to it,
Huh?
some stiffness.
Yes. Then I know a little about it. The top having a different structure to the bottom. That's the basal. A lot of pictures were in the research paper itself, which explained the radius and the curvatures itself.
I mean, I think this is not impossible. You're going to have cells that have a lot of voxels. They'll be big, right? You'll have to have a lot of, to get the spatial resolution you need, you'll have to have a relatively large cells. But I think, I mean, this is a problem people have wanted to look at for a long time. So I think it's quite interesting. For the first one problem is that CompuCell does not have a curvature energy. There's no energy term in that's available. There's no energy plug-in that monitors the curvature of the surface of a cell. One could imagine doing that in a variety of ways. Giuliano has the idea of having membrane-bound proteins simulated. They could secrete a short-range chemorepulsion or chemorepeller or chemoattractant that could provide a force that leads to curvature. So that's something one could explore. You could do that even in 2D, where you have a molecule, a compartmental cell, where the cells have a component that secretes either intracellularly or extracellularly. That intracellular or extracellular component push on the membrane. And I believe if you explore that, you should be able to get these kind of curved shapes like the ones you see in the figure A at the bottom. And one could explore that. That's already something people haven't done. So by itself, that would probably be a 2-day project, but it could be very interesting. And if it worked, it could be quite powerful. The other thing to do would be to actually design a plug-in that actually measures the curvature of the surface and has an energy penalty associated with that for a target curvature. That might be a little bit more challenging computationally. You could develop it in Python, but eventually it would have to be implemented in C++. But they're both great projects. I think interesting.
For the okay, if one should explore using the membrane-bound protein, will it give the regular shapes in the basal also?
Sorry, I'd say that again.
Okay, I said if one should use the suggestion you made, which is the membrane-bound protein, I'm asking if will it also produce the irregular shape we have at the basal surface?
Well, then the question is, why is it irregular at the base and not at the top?
Okay.
But I'm just asking the question, could you build a cell that wanted to have that invaginated shape that you have there? And I think the answer is yes, but it would take some work to do it.
Okay.
Just in a section, just in 2D to begin with.
Okay. Okay. I'll try it out again and see.
I might look at papers that Sharon Lumpkin has published on curvature, on origin of curvature. She didn't use CompuCell, but the ideas should be relevant.
Okay. It's a Sharon Lumpkin, right? Sharon Lumpkin.
Sharon Lumpkin at North Carolina. Sorry, I didn't mean to. I tried to turn my microphone on and I hit the
You're muted again, James. Oh, okay.
Sorry, there was something in the background there. So I think that this is a great problem, but it does require, again, like Sharon's problem. But that's why we wanted to have these discussions early, so people could take these great ideas and begin to make them a little more precise before the hackathon.
Sorry to move on. Any other questions from anybody else for Akamwali before we move on? All right, sounds good. Thank you.
Okay, thank you very much.
I know Alsami and Mohammed had their hands up before. Mohammed, did you want, I know you've talked a little bit today already. Did you want to give, did you have a more formal presentation you wanted to present about your idea?
Can I talk? Hi again. Thank you for the presentations, and thank you for this meeting. Actually, I have the old presentation 2 weeks ago. I already presented, so I was hesitating to present it, but I already uploaded to the drive, the folder, shared folder that's Hayden sent. Anyone can see it there, and I also can present it again. You can talk about it. We can see what we can. I can share my screen. Okay, before that, I wasn't so sure about the reaction diffusion systems, PDs, in terms of modeling and in terms of numerical simulations or just simulations in CompuCell. So as James offered me to work, maybe we can produce a kind of educational project, like like solutions of PDs in CompuCell, and some models, like known models like Schneichenberg model, and some more complicated models, including some more complicated biological processes. So this is what I would like to do actually in this workshop. First, I would like to see if I can replicate the existing models, and if I can see how the reaction diffusion systems can be simulated through this environment. And if it is possible, I would also like to model reaction diffusion systems, including more complex issues, like more complex biological issues like cross diffusion, domain growth, or cell mechanics, and like that. And I also, this is for the further steps. It's if possible for modeling cell migration and modeling mitosis and domain growth might be the next questions. So I mentioned about the pattern formation in nature. This is what I'm currently doing. I'm working on existing mathematical models, and I'm doing analysis. I have background in PDEs, partial differential equations, especially reaction diffusion systems in terms of stability analysis and some sort of numerical computations, such as finite element methods. This is what I'm currently working on, and I'm using Phoenix, and it's uses a lot of Python, and I have some experience on Python. I also want to tell about it. I also want to see the geometric effect of the reaction diffusion systems on some more complex geometries, especially 3D biological surfaces. And as I told you, I have PhD in mathematics, and I am looking for potential teammates who especially has experience in computational cell 3D or Python. or I am open to any kind of suggestions that Hayden and James can provide me to. And for the replications, I am also interested in such sources, especially number 18 here. And there is also one another. And if time permits and for the future, maybe, I would love to see how things are going in these papers. So I also want to say that this is also posted to the drive. So this is what I can say for this presentation. Hello.
Okay, that
Mhm.
sounds great.
Ah.
That was very nice. There's a lot there.
you.
Again, I think the angelfish PDEs would be not a bad one to try putting into CompuCell. And as I mentioned, I think the last time when you're doing these PDE models, you can start with the pure PDE model.
Mhm.
Then you have the cells read and respond to the chemical species. At first, they just read it. So you make tracking fields to make sure that you can have the cells replicate the fields that the PDE generates. And then gradually you make the cells do more and more. So then eventually you get rid of the original fields and you have the cells generate and respond to the fields. And then it's easy to put in cell growth and division. And so then you get growing domains. So it's possible to do all of those things. Making it work numerically in a reasonable amount of time isn't so easy. But theoretically, it's easy to do that. And so, and I think the angelfish is a great problem that way. Now you could do other examples as well, but the angelfish one is one that is pretty good. You probably are going to have to make the diffusion length shorter, so that the number of cells is fewer than in the real fish. But that doesn't change the basic principle.
I am sorry, the last sentence I couldn't hear because I think my internet is just cut.
You probably will have to make the diffusion length shorter, so that the number of cells per stripe is fewer, so that the simulation runs faster. Because in the angelfish, the stripes are quite wide in terms of number of cells across the stripe. And so that makes it a little more expensive. But conceptually, this is a good problem. We had some students who worked on zebrafish stripe generation last semester. They didn't finish it, but that was a realistic problem. They were using the work of Alexandria Volkaning, published a nice paper on the zebrafish stripe mechanism using a different package. That would be a nice place to start, perhaps, on that. So you might, if you haven't looked at her work, you might want to do that.
Is this paper in the list of the papers that you put it?
I don't know. I'd have to. It's a long list. Probably it may well be, but I'll put her name in the chat.
That's perfect.
You can find her. You can find the paper. Hers is on zebrafish stripes, but it's very similar mechanism to what you have in angelfish.
Yeah, I'd like to ask a clarification question, if that's okay. Can I do that? Okay, so Gulfemi, a very, very nice presentation. I'm just trying to understand your focus as far as your background goes. Are you interested in modeling systems with PDEs, or are you interested in numerical solution of PDEs, or both? What's your emphasis?
I am actually interested in both. It's also some kind of necessity, I can say, because you always need to ensure that your theoretical observations, it needs to be clarified, and it needs to be like strength with the numerical. This is what I can say. But at the moment, of course, we can we can initiate a starting point if we are working as a group. We can start at one point and we can move step by step.
So which area do you want to make contribution in? Is it the formulation or the numerical solution? I guess that's what I'm trying to drive at. What's because at some point, I mean, all these things that you're doing, you're going to want to publish, right? So then what will be the emphasis? What will you say that this is my contribution? I'm just curious.
Mm-hmm. Actually, for the publications, I didn't think about at this stage. First of all, I want to get this skill. It would be nice for me to see because it's not easy to work on some complex models, reaction diffusion models, when it's given on, especially for a very complicated geometry. So it might be nice to see it, to see what the availabilities and abilities that I can do in CompuCell. But of course, the publications would be nice. I'm doing research, and I would, of course, would like to contribute the area as much as I can.
Hi, Gulsmay. This is Mokishwar. I'm from University. So I was just wondering, do you want to take like a persistent homology kind of approach?
I'm so sorry. Can you repeat again?
With respect to your model, do you want to take more of a persistent homology kind of approach?
Well, more about pattern analysis once you have the pattern, right?
Pattern, you mean the pattern formation eventually? So
I think maybe I shouldn't interrupt, because maybe everybody was understanding each other. There was a question about a particular kind of numerical analysis to do on the pattern to try to classify the patterns. Which Alexandria Volkening has been very involved with.
Yep. Yeah, exactly, Dr. Glacier. Thank you.
So there are two steps. One is generating a pattern like the stripe pattern.
Mm-hmm.
And the other one is, once you have a stripe pattern, how do you characterize the stripe pattern? How do you quantify the stripe pattern? And so if the stripes are completely regular, then it's not so hard to quantify them. You measure the space between the stripes, or the width. But if the stripes are irregular, as in many fish, then it's not so easy to quantify the pattern. And if you have two patterns, you want to ask the question, are the patterns the same in some fundamental way, or are they different in some fundamental way? And so the question was about a method that Alexandria and others have developed to try to say, are two random patterns the same in some fundamental way? And so if you look at the papers of Alexandria, she has some papers generating models which produce patterns, but she's also worked a lot on how do you analyze those patterns. And so I think there was a suggestion that once you have the patterns, it could be of interest to try to think about how to quantify them. Is that fair? Is that what you were trying to address?
Yeah, pretty much, Dr. Glacier. So I was interested in knowing how you were going to study the patterns, and specifically if you want to quantify them. So in case if you're interested, I have dropped in like two GitHub packages, Ripser and Rivet. So Rivet is like a 2-parameter persistent homology system, and Ripser is for specifically identifying patterns in your system. So this is pretty much from Dr. Volkening's previous lectures. So if you're interested, you can go into GitHub and mess around with the code that they have inside.
Thank you very much for sharing these links. Actually,
no problem.
As James pointed out, we might have not always, we might have transitions from stripes to spots or stripes to circular stripes. So it is also important mathematically. We have actually tried to do it with finite element methods, like to see if there's a transition and if the transition is stable. I mean, if it's for the long-term dynamics, if these same kind of patterns we have, or the patterns are changing, oscillate, like we have time oscillations. So, or that kind, if this is the question, yes, those are, I think, important points to check. And I thank you so much for the links. I want to save the links. Yeah. And I also want to check the papers that you gave me, James. Thank you so much. Yeah. We have done it so far with only by checking some numerical analysis, but this might be really also a problem that we want to see how patterns behave in the long-term dynamics.
Great. That's a great, they're both great. They're all great problems that have been brought up. So I hope people will be interested in these and join these groups because they're all great topics.
Thank you. Thanks so much. And if we could able to systematically bring it to a place, and I would be, I'm willing to maybe an educational project that you last time mentioned.
Yep, that would be something that I in particular would be interested in as well. So we'd be perfectly happy to work with you on that. If it gets to that point. So, all right, so we've got a few some people here who were not here last week. Was anybody else interested in either giving a quick lightning talk or in asking some questions about a project idea they have?
Hi, Hayden. Would you mind if I go ahead next?
Yeah, sure.
Yeah. So mine was pretty much a last time presentation. So if I just have bullet points, don't mind jumping in and asking for details. I would love to elaborate on that. Okay. Can you guys see my screen?
Yes, we can now.
Okay, cool. Oops. Hi, this is Motishwar Jairaman Krishnan. I'm a master's thesis student. I'm associated with Dr. David Emilis and Dr. El Shepinar. So I'm trying to model the I'm computationally trying to model the calcium activity in zebrafish tail fin and the wound healing process. So it's just pretty much like a general wound that occurs in any human or any system that we are looking at. So we have epithelial cells and there's going to be an wound. And we want to see how the external wounded cells communicate with the healthy cells to generate a calcium wave. So this is pretty much the biological background I would like to impart in the whole process. So we have an ODE-based multi-scale model that we are interested to build. And we want it to communicate between cellular to tissue level, and it has to generate a calcium wave after the zebrafish tail fin injury. So if you see the figure at the right side, so there is an injured zebrafish tail fin, which is trying to propagate an instantaneous calcium wave, which ceases over time. With respect to modeling this whole project, we have been taking approaches with respect to reproducing, like approximating Dr. Zotman's Drosophila winged system. If you're aware of it, I would like to provide a detailed approach later on. So in that system, we had intracellular communications, but no extracellular communication. So we thought we would research more on like the current approaches and the recent strategies. And with respect to the experiments, we found that there are no specific transient waves that occurs in calcium with respect to zebrafish. And we have the figure on the left on how the epithelial cells behave during an injury. So we have the damage associated molecular patterns and calcium immediately showing up in the system. So we are specifically interested in studying the detection phase of a wound, and we would later on go ahead and see how the tissue regenerates or the wound responds to multiple stages. So this is our problem motivation. So we have been using this system specifically. So there's going to be an injury, and GPCRs are going to be our receptors, which are going to have agonists which bind to them. So in Dr. Zartman's paper, we saw fly extracts trying to bind to the receptors and then creating the whole cascade of events, how phospholipase beta is being generated and how it cleaves PIP2 into IP3, and then how IP3 binds to IP3 receptors. But IP3 receptors are going to take out calcium from the ER to the cytoplasm, and then CIRCA is going to complement it by taking calcium from the cytoplasm and putting it back into ER. So in this due process, he also had some concept called as initiator cells and standby cells. So if you see the cell I, we consider them as initiator cells, and cell J would be our standby cells. So in the initiator cells, there's going to be the whole cascade of events happening, and then there's going to be a flux of IP3 and calcium, which will be exchanged through the gap junctions through cell J. When trying to reproduce this with respect to equations, and like he previously had ordinary differential equations, and all we had to do was to tweak some parameters and change the values to get the waves. Because in his whole system, he had 4 different types of calcium activity, including bursts, transients, wave, and fluttering. But we were just interested in the process where waves were occurring. So this is the window of calcium, and this is the window of agonist. So agonist fly extract is trying to bind to receptors up here, and it's going to produce calcium from down here. We were able to work with the agonist, and we were able to get the levels, and we were able to get the model to reproduce a wave, but it didn't do it as well as we thought, because it is able to propagate the signals from initiator cells like the cut point to the standby cells, which is next to it. So after that, the neighboring cells could not generate the whole wave. Troubleshooting this process gave up like a new idea over here. So we have ATPs and how ATPs bind to receptors, and then bringing in extracellular calcium into the system that we are going to model. These are the 2 main or the new approaches that we'll be taking in. And this is based on Dr. Huang, and this is based on Dr. Politi. So these papers have been also simplified by Dr. Zartman's group to get it working for the Drosophila system. One interesting aspect here is, so we are only interested in seeing one single pathway on how phospholipase C goes into cleaving PIP2, IP3, and then calcium from ER to cytoplasm. So in previous models, we were studying more on the intracellular approach. Now we are more interested on the extracellular approach, how the tissue is going to get damaged, deformed, and how they are going to spread out calcium and ATP all throughout the system so that individual cell grids would be able to signal through for the whole process of calcium wave formation. And going through forward, so the major impact that we are expecting is, so we want to reproduce Dr. Politi's paper with respect to the ATP model by Dr. Huang. So it's like 2 big concepts, like it's like Lego blocks, and I want to merge them together. So we have this paper, and we want to bring in concepts and get the equations so that we can build a CompuCell model and see the tissue-based calcium wave that we are interested in. So values and the system are basically the same. So we are just trying to see how the equations or the parameters behave specifically. And based on experimental data, we also know that there is a necessity for extracellular calcium wave to make this model behave perfectly. So again, why we need a quantitative modeling is because with respect to experimental data, we fall short with some of the readings. So it's either the ATP or the IP3 or the calcium. It's something which triggers another one, but we fall short with respect to connecting the parameters. So we are interested in creating a quantitative model because we want to see how they are going to communicate with each other and how every single level in a factor or a parameter will individually affect the whole system. And we are currently just looking at the cellular level and the tissue level. So we are going to create ODEs specific to a single cell, and we want to see how they behave over the whole tissue. So every single cell will be encompassing an ODE in this process. And we are trying to predict how the instantaneous wave of calcium is being produced. Like I showed you guys in the figure, like the first figures, so we want to see how that wave is being produced, and thus, is there any specific factor that causes this whole process? And yeah, so our hypothesis currently is, does the presence of extracellular ATP and calcium affect the propagation of the calcium wave? So that's our major hypothesis. And over this process, we want to see, like, if we successfully build this model, and if I get this done, I would want to study how the wound healing and tissue regeneration occurs in the future. And I would also like to connect this model to a subcellular, pretty much we are like flowing around subcellular processes, but I want to completely connect it to a subcellular level and to an organ level to make it like subcellular, cellular, tissue, and organ level, like a complete multi-scale model that we are all interested in. And then with respect to the feasibility of the project, so the diffusion and individual cell grid dynamics play a vital role in the propagation of this calcium wave. So we need every single cell to, it's like, imagine it like rows and columns, like just matrices. And we want to see how every single row and column interacts with each other to produce us like the eigenvalues. I'm just making it just mathematically possible. So coming from biological perspective, we want to see how an external distribution of ATP and calcium. So consider this as the cell, and there's a cut. And we want to see how the uniform patterns from the expulsion of ATP and calcium would go into individual cells and create a wave. And yeah, what are our inputs? It's basically extracellular ATP and calcium. So that will be our major agonist. And then we'll have phospholipase C synthesis levels, which will be our secondary agonist. And then moving further on, we'll also have our outputs, which will be the exchange of calcium between extracellular space and the cytoplasm, and then exchange of calcium between cytoplasm and endoplasmic reticulum. In the due process of our project, so we are planning to, amalgamate these two models and create equations, and then put them into CompuCell3D and see what it specifically does or how it behaves. That's pretty much how we are going to work through. These are the references and resources that I'm using right now. So this two will be our parent articles by Dr. Huang and Dr. Politi. And we can also cross-verify or like every single stage or step process by going through Dr. Zartman's paper back again to see how we can change the model or how we can tweak the parameters in the due process. So my current teammate is Norma Perez. She's also a postdoc here with Dr. Emilis and Dr. Hayden. And so we have a decent background with cell and molecular biology, developmental biology, and mathematical modeling. So we want more of a biomechanical perspective and a strong coding and debugging background. I would appreciate somebody with a great Python programming background. And once we are able to simulate like kind of oscillations, we can pull it on together into CompuCell and see how the whole system behaves. Welcome for all questions and suggestions. Thank you. Yeah, and feel free to email me through my email ID. Yeah, that's it from my side.
Yeah, looks like James just posted a comment to the chat. I don't know if he has any follow-up comments.
I mean, that's a great problem. I mean, there are a couple of different things that you proposed. One of them is changing the model structure. One of them would be looking at how the wave speed or the distance it propagates before it dissipates depend on parameters within the original model. For all of those, you're going to need to have some kind of cluster execution, because you're going to need to run a lot of replicas and do parameter scans. And so maybe one of the things that would be helpful would be to look at, what before we start in the hackathon, look at what HPC resources you have at Purdue, so that you could run a parameter scan, get CompuCell running on those, so you could do parameter scans. You could talk to TJ about some of the parameter scan structure that he's developed, but the problem is it's a little bit different for every cluster, and so you'll have to do a little bit of adapting for that. And then you'll have to have some way of quantifying the results when you run the simulation. You'll have to have some output, which is, how fast did the wave go, or
Like the time frames.
How far did it propagate? So you'll have to have some metric on the output of the simulation to quantify how good the simulation is in some way.
Yeah. I would like to see how the whole system behaves when I create these, like, because I don't have the parameters from the extracellular system and for the ATP. So bringing in those equations would create like a different kind of cluster with respect to what I already have. So yeah, looking forward how it's going to work. So thank you.
All right, so we are running up on time here. Is there anybody who wanted to give a last very quick presentation of an idea, or anybody who has any lingering questions about hackathon details?
Yeah, I have a quick question. It's trivial. I probably know the answer, but I want to know it from your end. Can a person belong to more than one group?
We don't recommend it. There's generally not enough time for that. I mean, I guess, I don't know if we've ever really had that in the past. I suppose it depends a little bit on your role in the group. So if you are, for example, like maybe a Python expert, and people need help implementing things sort of on the spot in Python, you may be able to bounce from group to group. If you are, the biological expert for the group that is in charge of, helping people understand how to turn the biology into a computation, that may be difficult to work in multiple groups because that's sort of a more intensive role. But if you do have a more technical role within a group, you may be able to kind of move between groups. But in general, that it's very challenging given the time limits of the hackathon.
But have you seen it in the past?
We didn't have any last year. I don't know about James, but I think we may have had one person last year that switched groups after day one. I don't remember exactly, but it was kind of like the group they were in was too big, and so they were moving to a smaller group where their skills would be more useful. But it wasn't like they weren't moving between groups more than once. It was more of a one-time shift. I mean, if you're potentially interested in trying that out this year, we can think about it. But it's like I said, it will depend on the importance of your role within the groups you pick.
Okay, thank you.
Yeah, because we wouldn't want you to be in one group where you're, kind of in charge of helping people understand a lot of things. And then, for half the day you move to a different group and that group is kind of left without, one of their organizers, if that makes sense.
But it happens. Sometimes an organizer will drop out or two groups will merge. One reason we want people to present at the very beginning and then at noon on the first day is that way if it's not going well and you want to switch groups, you have the opportunity to do that. So I think it's I mean, again, we're not trying to tell people what to do. All we can do is give you the advice based on the experience we've had in the past.
And there is also the option, if you would like to participate in the hackathon as more of a support role who can help move from group to group, maybe answer some questions, we can talk about that, but that'll obviously depend on your current levels of expertise and things like that. So if you're more interested in moving around the room as kind of a TA as your hackathon participation, we can talk with you about that. But yeah, it'll just depend on what groups you're in and what your role is in each group as to whether or not bouncing between groups makes sense.